you can see here, we start with the one with the triple bond, and then in the end, the triple bond is gone. We see the one bromine. So definitely we have added the HBr, right? But that's not the only thing added. If you're adding HBr, just one molecule to the triple bond, you still have to have a double bond. But this is not a double bond there. So that means we also added hydrogen too. So these are two reactions put together. We need to do the hydrogenation, we need to do the HBr additions. I mean, once you figure that out, then how do we add an HBr? That would be basically just adding HBr. I mean, at least you can control how much HBr is being added. So let's say you're just adding a one equivalent, meaning the 1-to-1 ratio. Then the proton is going to be adding the lesser substituted side. That makes a binding cations on the more substituted side. That bromide capture that position, then you get the bromine on the more substituted side. That's a Markov product. If you have this bromine on the less substituted side, then you have to do it in an anti-Markov fashion. That means the HBr being added in the radical condition, right? So you got to choose the right reagent for that. But adding one HBr, you get the bromine on the more substituted side, still have a double bond. So adding hydrogen to double bonds, yeah, you can do that. Hydrogen gas with those precious metal catalysts, then you can do this. This is a kind of a, if you decide to add an HBr first and the hydrogen later. Can you switch the order? If you switch the order, let's say you do the hydrogenation first, then in these reagents, you cannot control stopping in the middle. One hydrogen gas will be added, then there will be another hydrogen be added, you're going to be fully saturated. So you cannot switch it just as they are. You got to use a different reagent for doing that. But thankfully, you know the poison catalyst can manage to add just one hydrogen molecule. That's a lindless catalyst. It stops at the double bonds. This time, we don't really need the trans or cis geometry. That's not really necessary. So you can do it even with a sodium in the liquid ammonia. Either way, that triple bond will be converted to double bonds. Then you can add an HBr addition. This one's the same HBr addition as before. So it's just a different way of doing it. You can add an HBr first and the hydrogen later. But the thing is that if you want to do it the other way, this is not the way to do it. You've got to do it a different way and then adding up your HBr later. If you ask me which one I favor more, I mean, I would pick both answers the same from here because we probably don't know the detail of the, all the things that you need to do to make things. But if you ask me which one I favor more, I would pick the second route. The reason is, if you do this way, controlling 1-to-1 ratio is actually more difficult. So why is that? Well, simple thing. Let's say you've got 10 of you there, and there's a 10 sandwich on the other side. And I'm asking you guys only pick one, but if I'm not really watching it, I'm pretty sure some of you two, some of you get none. That's what happens to the molecule. Some molecule, even though it's a 1-to-1 ratio, there's no one placing it. So some molecule will get 2 reagents, some molecule will get no reagents. There's going to be a mixture there. That's kind of what makes it difficult to control this one. So that's why, I'm not expecting you to know that, but that's kind of a trouble reaction that I see from my point of view. Because if you got the multiple things made at the same time, you have to separate that. You really only have to create this one carrying forward the next reaction. And the separation of the molecule from the other molecule, that's what makes it challenging. That's really makes it difficult. So this way is a lot more control. So I'm more favoring control. This, the Lindler's catalyst is just adding one molecule. It doesn't actually, no, not by accident. So that way you can only get the double bonds. And then this one, even though you get excess of HBr, only one will be added. So a lot more you can control that. So that's the reason I favor the second one. I don't know why I'm telling you this, but some of you may be interested in carrying, pursuing the organic chemistry in your career, then this is something you better know. All right, so that is basically that. These questions are pretty simple, right? The reagents are actually telling you what the reaction is now. And that's kind of a thing different from the second test. Second test, I know this is kind of tricky because you got the similar reagent, but now you need to figure out what's going to happen. So that's kind of what makes it disoriented. But this now, it's a lot more straightforward. If you know reagent, you know what reaction that will be. You still need to worry about other things, like biochemistry, stereochemistry, and things like that. But at least you know what reaction we're talking about. The mercury sulfate, the triple bond, that's basically adding water to triple bond, right? So the mercury will be added first. That will make a vinyl cation. That capture the water. So that will make a enol. But the thing is, sure, enols be produced, but that makes a ketone in the end. That's an enol ketone tautomerism. What I'd like to tell you that is, if you answer that, you'll get 0 point. No, you'll get partial credit, but you're not going to get a full credit. That's the thing. And if you work it out to get this bar, then just work out a little more, knowing that the enol is not for one stage, it changed to ketone forms, then you get the full credit. So this is something that the difference is that you want to know. And believe me, we always ask this question. If you do this with hydroboration reactions, but not the BH3 to triple bond, because the BH3 are too small, and then it can react multiple times to triple bonds. So we using vertiborane, something called the dicyanoborane. That way, only the one hydroboration will be done, and then make sure that you have the anti-multiple products. That will put the boron on the lesser tryptophan side into terminal conditions. That boron will change to OH in the second step, so you get the enol again. That will be tautomerizing. These become a double bond that get the protons. You get the alcohol because it's terminal conditions. So you can see that your end product is different, even though you get water added over time of the treatment. So this is something that you gotta make sure that you know it, so you don't get the right answer. This one is basically you recognize this is a aldehyde. You need to make it from the triple bond. That's not something that each to recognize. Retrospective analysis is a little bit difficult because adding water makes an enol, but enol change the ketone forms. That's a little bit difficult to analyze in the backbone. So this is kind of something that you have to recognize. You can see that this is a kind of something that is produced by the hydroboration reaction on the triple bond, because that way the end carbon of the triple bond becomes an aldehyde. And this is kind of because of one of the backbone, one of the tricks you asked. The more tricks you know, actually you can figure out things easier. That's the reason why organic chemistry requires some memorizations. And this is kind of one of the cases. It's not easy to make a relation between these two. I mean, the enol is definitely makes sense because of OH is added, and then it's an addition of the water. But because enol changes the forms of ketones, when we show just products and the starting material, unless you know this reaction, it's really hard to make a connection. Because how come it makes an aldehyde, right? So that's the reason we always ask the question. It's something that you really need to know. How it goes? Well, same way. The disalmylborane is a basic big alkyl borane added on the less substituted side, which is the hydrogen substituted side, and the hydrogen on the more substituted side, added together, make this. That will be replaced by the OH in the end. That's amino that tautomerize, meaning that the carbonyls are created between these two, that get the proton, makes it out. So that this is some of the things that you probably need to memorize, I guess. The autolysis or the permanganate, the high temperatures are basically simple. It breaks the triple bonds and then either end becomes this carboxylic acid. That's basically very basic.